Okay, let's take roll. Hold on. Okay, so Bartram, Blair, Donnelly is here. Elwell, Levengood is here. Miller, Sheffield, Sullivan, Tillis. All right, so we're going to continue chapter 3. And again, this will be a bit of a recap from what you should have learned in your introductory chemistry. And that has to do with the whole concept of limiting reactants, all right? So in practice, let me share my screen first. How could I forget? Okay, so in practice, what you'll find is that in order for a chemical reaction to produce any amount of product, it's not enough for you to have stoichiometric equivalent amounts of reactants. So basically what that means is that you have to basically use an excess of a particular reactant in order for you to ensure that the reaction will take place, all right? So basically, you need to understand the difference between the excess reactant and what is called the limiting reactant, all right? The limiting reactant is the one that's not in excess, obviously, but the key thing you need to remember about a limiting reactant is that it is completely used up. And it is the reactant that pretty much determines how much product you expect to get, all right? So a lot of the stoichiometric calculations that you may engage in would involve you finding out first which of the reactants involved, if there's more than one, which of the reactants involved would be the limiting reactant. So once you identify which reactant is limiting, then all other reactants that may be present would be in excess. And therefore, as a result, as I said before, the limiting reactant will be completely used up. And then as far as the excess reactant is concerned, some of it will be left over, right? And the amount that is left over is dependent on the amount that has reacted with the limiting reactant. So, and here's another important point right here. The limiting reactant is not necessarily the one that is present in smallest amount. And that's because it depends on the stoichiometry, it depends on the balanced equation, and we're going to see some examples of that shortly. But to illustrate this whole notion, we're going to do a non-chemistry type of example, and then we're going to take the ideas from that to an actual chemistry example. So let's say you're given a task of preparing a packaged meal from this combination right here. You have one sandwich, 2 cookies, 1 orange, and therefore that combination will give you a packaged meal, all right? So we can represent that combination in the form of an equation, all right? So here's a situation that you have here. Let's say you have 10 sandwiches, 18 cookies, and 12 oranges. The question is, how many packaged meals can we make, all right? So what I'm going to do here is get out of this, go to my writing pad here. All right, so it's a sandwich plus 2 cookies. So these are my formulas for these items. Plus, what was it? A sandwich, 2 cookies, and what's that? An orange. I'm going to use OR, and that gives you 1 packaged meal. All right, so that's the equation, all right? Now, let me see here. So the example, okay, so you have 10 sandwiches, 18 cookies, okay. So you have 10 sandwiches, 18 cookies, and how many oranges? And 12 oranges, all right? Okay, and 12 oranges. So the question is, from that from those items that you have at your disposal, how many packaged meals can you make, all right? Now, based on the balanced equation here, we're assuming it's balanced. Let's say we look at things from the standpoint of the 10 sandwiches, right? So if you're going to use up all 10 sandwiches, according to this 1-to-2 ratio between the cookies and sandwich, you're going to need 20 cookies, right? But you do not have 20 cookies. You have only 18, right? So you know for sure, based on that fact, that, well, you won't be able to use up all the cookies because you don't have enough to use up to combine with the sandwiches based on that equation or based on the numbers. Now, in the case of the oranges, you have 12 oranges. Based on the ratio between the oranges and the cookies, if you want to use up all the oranges, then basically you're going to need 24 cookies. But again, you do not have 24 cookies, you have 18, right? Now, if you look at things from the standpoint of the cookies themselves, for 18 cookies, you're going to need half of 18 oranges, which will be 9, and half of 18, 9 sandwiches, right? So basically, these 18 cookies will use up 9 of the 12 oranges. So you're going to have 3 left over, and 9 of the 10 sandwiches will be used up by the 18 cookies. So therefore, you're going to have 1 left over, all right? So basically, the cookies in this particular case would be the limiting item. While the sandwiches and the oranges would be the items in excess. So I'm just going to put excess here, all right? So basically, it is this limiting item that will determine how many packaged meals you can make, right? And based on the ratio between the cookies and the packaged meals, you can see that there's going to be a 2-to-1 ratio between the two. So therefore, the total number of packaged meals that will be made would be 9, all right? And therefore, that's basically the whole idea behind the limiting reactant. In this case, it's not chemistry, of course, but it's the same principle involved, all right? Okay, so let me go back to this here because I think there's something else I need to make mention of. So basically, let me see here. If we were to express this mathematically, as I would expect you to do, I would say 18 cookies multiplied by 1 packaged meal over 2 cookies, and that will give you 9 packaged meals, all right? And then if you take a similar approach with the 12 oranges, and you want to find out how many packaged meals you're going to make from the 12 oranges, if possible, it would be a 1-to-1 ratio. So that would be 12 oranges. And then finally, and then finally, 10 sandwiches. Again, we do a similar approach. And that will give you 10 sandwiches, right? So this is another way of determining, there should be packaged meals here. All right, this is another way of determining which reactant or which item is limiting. By virtue of the fact that you did the calculation to figure out how much or how many of the packaged meals that can be produced, the one that gives you the lowest amount on paper, that would be the limiting reactant. So therefore, based on this calculation, we can say that the cookies would be the limiting reactant, while these items will be in excess, all right? Okay, so that's a non-chemistry demonstration of the whole concept of limiting reactant. Now we can, of course, take the idea that we have just learned and apply it to an actual chemical reaction. So what we're looking at here is 2 compounds. One is known as ethylene, reacting with bromine to form a compound known as 1,2-dibromoethane. And the equation for that reaction is C. Okay, why is this not right? Hold on. Okay, let's see if this works. C2H4 plus Br2 to give C2H4Br2. All right, so this is a simple reaction, 1-to-1-to-1 mole ratio between the reactants and products, all right? So in this particular case, you're given 28 grams of ethylene, which would be 1.0 moles, and you're reacting it with 0.80 moles of bromine. So the question is, how much of this would you expect to be formed? So because this is a 1-to-1 ratio between the ethylene and the bromine, we can easily predict that the bromine is going to be the limiting reactant. So therefore, all of this would be used up. So I'm going to put minus 0.80 moles here of the bromine, because all of it will be used up. And because of the 1-to-1 mole ratio between the bromine and the ethylene, the change here for the bromine, for the ethylene would be the same, minus 0.80 moles. While the change here for the C2H4 would be plus 0.80 moles, right? Because you'd have started off with 0 moles of that, right? So at the end of this reaction, you're going to have none of that, no bromine left over. You're going to have 1.0 minus 0.8, which will give you 0.20 moles. And here you're going to have 0.8 moles of the ethylene dibromide. So basically, this would be the amount of the product you expect to get. And when you convert it to grams, you're going to get 150 grams. Of course, by now you should know how to do that. And unfortunately, I wrote over this box right here. So let me clear this right here so I can read it. Okay, why is this not clearing? Oh, I'm using the wrong thing. Okay, so the question is asking, why is ethylene left over when we started off with more bromine than ethylene? Well, we actually answer that question because you can't just look at the masses themselves. You have to look at the moles and you have to look at the stoichiometry, right? 1 mole of the bromine, of the ethylene, is reacting with 0.80 moles of the bromine as a 1-to-1 mole ratio. That means that there'll be more ethylene left over. And the next question is, and we just calculated that the mass of the ethylene left over is 0.20 grams, right, of the C2H4. So the next question is, what mass of the ethylene is left over? So basically, all you have to do is convert this to grams. This is moles. We have to convert to grams. So you're going to have 1 mole of ethylene. And up here, you're going to have the molar mass, which you can calculate on your own. And then that would answer question number 2 right here. All right. Okay, so that's basically how that is done. So let me move on now to how do we recognize problems involving limiting reactants. First thing you need to do is that basically you need at least 2 or more reactants involved, and you need to be given the amounts of them, all right? And then what you should do, which is what we just did in a simple example, is that we perform a calculation to find out how much product would be formed based on the amounts of each reactant. And the one that produces on paper the smallest amount of product, that would be the limiting reactant, and therefore all the other reactants will be excess reactants. So, of course, the best way to demonstrate this is to go into an example. So let me copy and paste this here. And I think I'm going to use Word instead. So let me lasso all this here. And okay, so here's the question. It talks about magnesium nitride being formed from the reaction between magnesium metal and nitrogen gas. And there are two parts of the question. It says in the first part, how many grams of magnesium nitride can be made from the reaction of 35.0 grams of magnesium and 15.00 grams of nitrogen? That's the A part. And then the B part is asking, how many grams of the excess reactant remain after the reaction? Okay. So my question to you is, what would be the very first thing you would do in order to attempt this problem? Very first thing you need to do is what?
Balance.
Write a balanced equation. Okay, so what would be the reactants in this equation based on the information provided? Magnesium, okay, and nitrogen. What's the formula for nitrogen? N2, right? Remember, nitrogen is one of those gases that exist as a diatomic molecule. Okay, and then what would be the product? And what would be the formula for magnesium nitride? Not quite. Partially right. You're right about this part here, but you need a subscript here.
Magnesium 3, nitrogen 2.
Right, so the formula for magnesium ions would be Mg2 plus, and for the nitride is N3 minus. So you're correct. You need 3 of these and 2 of these, so therefore it's Mg3 and 2, all right? Then we need to balance it. So how would you go about balancing it? With a 3 in front of the magnesium, and that's it, all right? So that's the first thing you have to do before you can do anything else. When it comes to stoichiometry problem, balancing the equation is the very first thing you need to do, and then you can move on to the math part. Okay, so now we're going to move on to the math part. So in the A part, it says how many grams of magnesium nitride, which is a product right here, how many grams of this can be made in a reaction of 35.00 grams of magnesium and 15.00 grams of nitrogen. So what we're going to do is, as we just said in the PowerPoint, we're going to start off with a 35.00 grams of magnesium, and we're going to determine how much product you can get from that mass, right? So first thing we need to do is convert from grams of magnesium to moles, which means that you're going to have 1 mole of magnesium above, and then the molar mass of magnesium, which is 24 point something. 24.31 grams. That sounds right. I'll take your word for it.
I'm using the
Yeah. Okay, and then now we look at the mole ratio between the magnesium nitride, which is this here, and the magnesium. So what's the mole ratio between the magnesium nitride and the magnesium? 3 to 1, exactly. So down here, you're going to have 3 moles of magnesium. And up here, you're going to have 1 mole of magnesium nitride. And then we have to do the math. So let's see what this gives. 35 divided by 24.31 divided by 3. So according to my calculation, and please see if you can confirm this, because of course I am subject to errors, but this is what I got. 0.4799 moles of magnesium nitride, all right? And then now, we basically do something similar in the case of nitrogen. We're going to multiply this by, well, first we have to convert to moles. So you're going to have 1 mole of nitrogen above, and then the molar mass of nitrogen is 2 times 14.0, is it 1? 14.01?
Yeah.
So that will be 28.02 grams of nitrogen. And then we convert from moles of nitrogen, which is this right here, to moles of magnesium nitride. And you see that's a 1-to-1 mole ratio, right? So up here, we're going to put 1 mole of Mg, 3N2, and down here, you're going to have 1 mole of N2. And then we do the calculation for that one. 15 divided by 28.02 times 1. So that gives you 0.53 53 moles of Mg3N2. All right. So what we do at this point is that we compare this number to this number. And as you can see here, this one is the lower number, which means that it is the magnesium that is the limiting reactant, right? So that's basically how you answer the A part. All right, any questions about how we did the A part? Any questions? Any questions? Okay, so let's move on now to the B part. The B part says how many grams of the excess reactant remains after the reaction. So since we identified which reactant is limiting, that means that the other reactant is in excess, right? So what the question is asking for is how much of the excess reactant remains. So what we have to do first is to find out how much of the excess reactant reacted, right? So how do we do that? Well, let me get rid of all this here. What we have to do is start off with the limiting reactant. So the limiting reactant we just discovered, based on what we did in part A, is 35.0 grams of magnesium. And what we need to do is find out how much of it, how much of the nitrogen will react with it, right? So we do like we did before. We convert that to moles. We're going to have 1 mole of Mg, and down here the molar mass, which is 24.31, right? That's what we got it. That's what we used the last time. And then we look now at the mole ratio between the magnesium and the nitrogen. And I erased it, but if I remember correctly, it's a 3 moles of nitrogen to 1 mole of magnesium. So I'm going to put 3 moles of nitrogen above and 1 mole of magnesium below. And then the next step in this process, the final step, is that we convert moles of nitrogen to grams. So we're going to have 1 mole of nitrogen down here, and above you're going to have 28.02 grams of nitrogen above. And then we do the number crunching. So 35 divided by 24.31 times 3 times 28.02. And oh, something is wrong here. Wait a minute. What did I do? Hold on, let me do this again. I'm 35 divided by 24.31. Times 3 times 28.02. Okay, I did something wrong here. What did I do wrong? This is correct, right? 3 moles of nitrogen for every 1 mole of magnesium, right? Or is it the other way around? Oh, okay. I knew something was off. Yes, it was 3 moles. Okay, so this should be 3 here. I knew something was off. And this should be 1 here, right? Okay, so let me rework this. 35 divided by 24.31 divided by 3 times 28.02. Okay, now this is more like it. 13.45 grams. Now, please note, this represents the mass of nitrogen that reacted. All right? What the question is asking for is the mass, mass of nitrogen remaining. So how do we calculate that? We take the original mass of the nitrogen, which is the 15.00 grams, and subtract from it the mass of nitrogen that reacted, which is 13.45 grams. And whatever that gives, that would indeed be the answer. So it's 15 minus 13.45. So according to my calculations, this works out to be equal to 1.55 grams. And that's how you do that. Okay, any questions about this one? Any questions? Any questions? Okay, so what next? Going back to the PowerPoint. Okay, so another thing that we need to be concerned with when it comes to reactions, and again, this is a review of what you did before, is what we call the yields of reaction. And the reason why this is important is because even though one may do, let's say, a stoichiometric calculation to find out how much product you expect to get based on the given amounts of reactants, in practice, very often you don't get what you expect. In fact, you'll get, in most cases, less than what you expect to get based on your calculation. So at this juncture, you need to be able to distinguish between what is known as the theoretical yield, which is, as I said before, the amount of product you expect to get based on your stoichiometric calculations, and the actual yield, which, as the name suggests, is the amount that you get directly from the experiment, right? Ideally, in a perfect world, the actual yield would be the same as the theoretical yield. In practice, however, that's not the case, right? In practice, I would say in most cases, what you'll find is that the actual yield would be probably 50% or less than the theoretical yield, which leads us to another term, percent yield, right? This is oftentimes used as a measure of how successful the reaction is quantitatively. Percent yield is the actual yield divided by the theoretical yield times 100%, right? In a perfect world, 100% yield is exactly what you would try to get. But again, in practice, not so much, right? You'll probably get, in fact, I would say that if you get anything above 80%, you're doing pretty good as far as chemical reactions are concerned. And there are many reasons why the actual yield is less than the percent yield, right? For one, and you may want to write this down, one of the reasons why the actual yield is less than the theoretical yield, or why the percent yield is less than 100%, is that you might have what are called competing reactions. In other words, the reaction that you're performing will take place, but you might have another reaction using the same reactants, which would also take place, and therefore that could cut down on your theoretical yield. Another reason is that some reactions are reversible. In other words, the product of the forward reaction can itself react to get back to the reactants. Another reason is that the products themselves will react to form other products. You see what I'm saying? So there are many, those are just three of the reasons that readily comes to mind, which basically results in the actual yield being less than the theoretical yield, all right? Okay, so here is an example of a reaction between, and this is actually another example of, actually, it actually touches on some of the things that I mentioned a while ago. So let's say you're trying to perform this reaction here. Let me write down the equation somewhere, see if I can squeeze it in somewhere here. So this is the reaction you're trying to perform here. Zinc plus sulfur to form zinc sulfide, right? And to balance this, you're going to need 8 here and 8 here. So this is the reaction that whoever this is, this person who is trying this, he or she is trying to basically make only this product here, right? So you mix the zinc with the sulfur, you heat it up, you get a nice exothermic reaction, and then everything cools down and you examine your contents as far as your products are concerned. And what do you find? You find not only do you get what you want, but you get another product, zinc oxide, which is a competing reaction, or the result of a competing reaction. Because not only does the zinc react with the sulfur, the zinc reacts with the oxygen from the atmosphere, right? So basically that in and of itself will cut down the yield from the theoretical value to what you'll actually get. You also will have unreacted zinc. In other words, the reaction may not go to completion. We're assuming that we're using stoichiometrically equivalent amounts of the zinc and the sulfur. And sulfur also would be present as well. So basically the reaction doesn't go to completion. It's possible that the reaction could go in the reverse direction. And that's the reason why not all the zinc and sulfur reacted. All right, so that's basically just one simple example of a reaction where the actual yield is less than the theoretical yield. Okay, so based on what we have covered so far, you should now be able to do oh, by the way, oh, no. Okay, I think I remember doing that. Okay, so I want you guys, assignment number 3, chapter 3, right? I want you guys to do question number 11. And question number 12, 11 and 12, all right? 11 is based on what we did for this example right here, right? If you understood what we did here, then it's pretty much the same process. The only difference is the numbers and the equation will be different, all right? So I want you to work on that right now. If you have any questions, feel free to ask, because that's what I'm here for. What's up?
So.
Mhm. Oh, okay. So, well, the products would be NO2 and H2O.
So it'd just be, just.
Right, I'm gonna put them over here. Oh, and I just realized there's a typo, folks. Where it says how many grams of NO, that should be NO2. All right, it should be NO2. No, hold on. So after you write down the formulas for the products, you need to balance the equation. So you can't do this yet until you balance the equation.
Whenever we do division on this,
Oh,
usually it gives me a fraction.
oh, I don't, let me see here. I think somebody showed me this once. So if you divide 2.50 by, let's say 17, I think that's a molar mass for ammonia. If I remember correctly, is it this one? I think so. You press this key right here.
Okay.
Yeah, and it gives you the answer in decimal. I think that's it. Yeah.
Third of like those here, something have, NO2.
Where it says NO. In the question, it should be NO2. Hold on. You're Sullivan? Yes, sir. Okay. Oh, well, let's see if the class can do it. Let me bring this up on the screen. So it looks like some of you have been having a challenge of balancing the equation for this reaction. So let's see if we can do that together. Okay, where's my, I guess it would help for me to share the screen. Okay, so the reaction is between ammonia and oxygen to form NO2 and water, right? So how would you balance this? Anybody?
4 NH3 plus 7 O2. 4 NO2 6 H12.
Yeah, that looks right. Can we just check here? Yep, that's it. That's the equation. Okay, so let me look at the question here. Do I have a copy of it here? No, I don't. All right, so the question says that you're starting off with 2.50 grams of ammonia, and it's reacting with 2.85 grams of oxygen to produce the NO2 and H2O. So the question is asking which reactant is the limiting reactant. So what will be the first step in this process? I will start with the 2.50 grams of ammonia, right? What would you do with that? It's already in grams. All right, so you're gonna have 1 mole of ammonia. And over here, you're gonna have, down here, you're gonna have the molar mass. Yeah, that sounds right. 17.03 grams of ammonia. So this will go with that. And then what would be the next step? Mole ratio between ammonia and what?
By 2.50.
Well, that's this part here. But I'm asking for the next step. Now, in actual fact, you could look at the mole ratio between ammonia and NO2 or between ammonia and water. But I would choose this. And the reason why I choose that is because ultimately the question is asking later on how many grams of NO2 will be formed. So what's the mole ratio between the ammonia and the nitrogen dioxide? Exactly, 4 moles of ammonia and 4 moles of NO2 above, right? And then you work that out. So that's 2.5 divided by 17.03. So according to my calculations, I got rounded out to 3 sig figs, 0.147 moles of NO2, right? And then now we do the same thing starting with the oxygen, 2.85 grams of oxygen. Convert that to moles. You're going to have 1 mole of O2 above and 32.00 grams of O2 below. And then the next conversion factor would be what? The mole ratio between what? Exactly. So what's the mole ratio? 74. So what goes up top and what goes below? Okay, so 7 moles of O2 below and the 4 moles of NO2 above. And we do that calculation. So 2.85 divided by 32 times 4 divided by 7. And according to my calculations, I got 0.050. Hold on. 509. Okay, so based on our calculations, which one would you say is the limiting reactant? Exactly, because this is less. That means that this would be the limiting reactant. All right, so that answers the first part of the question. The second part is asking how many grams of NO, that should be NO2, is formed. Well, that's easy. All we have to do is take this value here and convert it to grams. So that's 0.0509 moles of NO2. And then we convert to grams, which means you're going to have 1 mole of NO2 above. And the molar mass of NO2 would be 14.01 plus 32. So this would be 46.01 grams of NO2. So 0.0509 divided by 46.01. Hold on, let me do this again. 0.0509 multiplied by 46.01. Okay, so according to my calculations, I got 2.34 grams of NO2. So that answers the second part, all right? And then now the last part is how many grams, no, I'm sorry, how much excess reactant. Now, if you remember what we did in the example I showed you, you should be able to do this part. So let me hear some ideas. How would you find the amount of excess reactant? Well, firstly, let me ask you, so which reactant is excess, is in excess? The NH3, okay, very good. So basically what the question is asking is how much of the NH3 remains at the end of this reaction. So let me Need a space. Okay, let me erase. Here. Okay, so basically, how would you determine the amount of ammonia that that has reacted? Let's start off with that first. Well, the question is asking how much of the ammonia remains. In order for us to calculate that, we need to calculate how much of the ammonia reacted. And then we subtract it from the original amount of ammonia to find out how much remains, right? So my question to you is, how do we determine the amount of ammonia reacting? Say the what? The original amount of what? But you need to find out how much reacted. Because you're going to subtract, you see, here's the idea. You're going to subtract the amount that reacted from the original amount to get the amount remaining. So the key thing at this stage is to find out how much of the ammonia reacted. And if you look at the example that we worked earlier, you'll see we did a similar thing. How did we find out how much of the excess reactant reacted? Well, let me give you a hint. We start off with the limiting reactant, which is the oxygen, right? And what do we do with that? I hate when this happens. How do I get over this crap? Okay. So what do we do with this value, 2.85 grams of oxygen? Convert to moles. So we're going to have 1 mole of O2 above and the 32.00 grams of O2 below. What will be the next step? This goes with that, by the way. What will be the next step? The mole ratio between what? NH3, because you want to find out how much of the NH3 reacted, right? Okay, so if I remember, what's the mole ratio? I erased the equation. 4 moles of oxygen. Okay, so 4 moles of NH3 above and 7 moles of oxygen below. All right, very good. And then what's the next step? And this will cancel with that. What's the next conversion factor? Exactly. So you're going to have 1 mole of ammonia down here. And up here would be the molar mass, which is 17.03. Right here. 17.03 grams of ammonia. All right. So let's do that calculation. 2.85 divided by 32 times 4 divided by 7 times 17.03. And according to my calculations, I got 0.867 grams. Is that right? Let me do this again. 2.85 divided by 32 times 4 divided by 7 times 17.03. Okay, 0.867 grams of ammonia. Remember now, this is the amount of ammonia that reacted. So what's the next step? Subtract what? Which is what? Minus the amount that reacted, which is 0.867 grams. And that's it. So according to my calculations, this works out to be equal to 1.63 grams. And that's it. All right? Any questions? Any questions? Okay, if there are no questions about that one, let me see what question number. Let's see here. Oh, question number 12 is a limiting reactant question. How would you go about? Okay, they gave you the reaction, the equation, and they gave you the amounts of benzene and bromine, the two reactants that you're starting off with. And it says if the actual yield is 56.7 grams, what's the percent yield? All right. So I take it it's okay for me to get rid of this here. Okay, so how would you go about solving this particular problem? The question is asking for the percent yield. It gives you the actual yield. Let me write it down here. The actual yield is 56.7 grams, right? And remember, to calculate the percent yield, that will be equal to the actual yield divided by the theoretical yield times 100%, all right? So basically what it comes down to is that we need to find the theoretical yield, right? Okay, so let me hear your ideas about determining the theoretical yield. This is the equation. And they gave you 30.0 grams of benzene and 65.0 grams of bromine. All right. So they gave you these amounts to start off with. So what would you do? Oh, what did I do here? Okay.
That reaction already balanced.
Yes, it's already balanced, so we don't need to worry about that. Yes, ma'am. Okay. All right, hold on 1 minute. Okay, so you start off with the 30.0 grams of C6H6. And what would you do with that?
You get the mole weight of C6H6.
Right, the molar mass, right? So that would be 6 times 12.01 plus 6 times 1.008. And according to my calculations, I got 78.11 grams of C6H6 and 1 mole of C6H6 above. So this goes with this. And then the next conversion factor would be what? The mole ratio between? So 1 mole of C6H6 down here. And what goes up top? And we work that out. So let's see what that gives. 30 divided by 78.11. According to my calculation, that gives 0.384. Okay, what next? Oh, this should be 1 mole here. So 30.384 moles of C6H5Br. Okay. What next? Okay, so 65.0 grams of bromine. We convert to moles. So you're gonna have 1 mole of Br2. And down here, we're gonna have the molar mass. So what's the molar mass of bromine multiplied by 2? I can't see it from here. Can somebody? What's the molar mass of Br2? Somebody with a periodic table. 159 point what? 0.8? Okay, I'll take your word for it. And then what would be the next conversion factor? What goes down here and what goes up top here? One mole of C6H5Br will go above, and down here you're gonna have 1 mole of Br2. So again, we need to do our number crunching. So 65 divided by 65 divided by 159.8. And according to my calculations, this works out to be 0.407 moles of C6H5Br. Okay, what next? Now that we have completed these 2 lines of calculation, what will be the next step? Right, benzene would be the limiting reactant because based on the calculations that we have performed, it would, based on that number, produce the lower amount of the product. Okay, how does that help us? Well, remember now, the aim is to get the percent yield. So we need to get the theoretical yield. So how do we get the theoretical yield? And the hint is right here. Exactly. So the theoretical yield is equal to 0.384 moles of C6H5Br multiplied by 1 mole of C6H5Br below and the molar mass above. So 12.01 times 6 plus 5 times 1.008 plus, what's the molar mass of bromine? Is it 79 point something? 79.9. Okay, so I got here 157.0 grams of C6H5Br2. So when I multiply that by 0.384, I got 60.3. So that's the theoretical yield. So to get the percent yield, where am I going to put that? Let me squeeze it in here. So the percent yield is going to be the actual yield, which is given as 56.7 grams, divided by the theoretical, which we just calculated here, which is 60.3 grams times 100%. Ooh. And let's see what that gives. 56.7 divided by 60.3 times 100, and the answer I got is 94.0%, which as percentage yield goes is very, very good. All right. Okay, what time is it? Okay, still have some time. All right, so that's basically how we do that particular problem. Let me go back to the PowerPoint here and continue our discussion of chapter 3. And now we're going to get into this whole idea of solution stoichiometry. And as the term solution stoichiometry suggests we're combining what we have learned just now with respect to stoichiometry to solutions, and in particular aqueous solutions, right? First, we need to remind ourselves of what we mean by the term solution. It's basically a homogeneous mixture of two or more substances. And of course, there are two parts to any solution. You have the solute and you have the solvent. And basically, the solute, if it's a solid, or I should say, if you have a combination of a solid and a liquid making a solution, then the solute would be the solid and the liquid would be the solvent. All right. Another term that I need to talk about, which I talked about in my lab class, but I don't think we got to it here in lecture. This whole idea of concentration of a solution. And it's basically the relative amount of the solute in a given quantity of a solution or solvent. And there are different ways of expressing the concentration. But basically, if a solution is very concentrated, that means that the amount of solute is relatively large compared to the solution amount. And if the solution is dilute, that means that the amount of solute is relatively small. So as you can see, these terms are relative terms. It's more important that we know how to quantitatively express these values. The most common way of expressing the concentration is what you see here on the screen. It's molarity. And this is the definition of molarity given right here. Mathematically speaking, it's in moles of solute divided by the volume of the solution in liters, all right? And therefore, as a result of that equation, we can say that we can express, I should say, the unit of molarity as, write it here, moles per liter, or we can use uppercase M, which is shown here, right? So whenever you see uppercase M, beside a number expressing molarity, you should remember that means moles per liter, all right? So that's molarity. There are other ways of expressing concentration as well. For those of you who plan to do Chem 2, you're going to learn some more, but this would be the most common way of expressing the concentration of a solution. So for example, if you're told that a solution of sucrose is 0.35 m, right? What that means is that for every liter of that solution, the amount of solute present is 0.35 moles. So therefore, the molarity is 0.35 moles per liter, all right? Now, key thing you need to remember, this is something that students tend to get confused about or misunderstand. Remember that this part here represents the volume of the solution, not the volume of the solvent. Very important. And that's important, especially when it comes to making up solutions of specific molarity. So here's an example of that. So let's say you're trying to make a solution of 0.01000 m potassium permanganate, all right? And there's a piece of glassware that is used, which if you were in my lab, you were introduced to it last week. It's called a volumetric flask, right? And this glassware is very accurately made. And as a result, it's very expensive, all right? They come in different sizes and they're basically used to measure a specific amount in terms of volume of liquid in it, right? You may not be able to see it. I don't think you can see it in this picture here. But in the flask, you have a mark which is etched on the stem, right? And that mark represents a specific volume, right? Depending on the size. So in this case, this is a 1 liter flask, which means that if you add any liquid up to that mark, then you have 1 liter of that liquid in it. So we tend to use this piece of glassware to make solutions from scratch, starting from the solute and the solvent. So basically what you need to do in this particular example is that you weigh the amount of the solute, which is equivalent to 0.0100 moles, which turns out to be 1.580 grams. And then you add it to your flask and you'd add some water to it up to about 1/3 or halfway full. And then you would stopper it and then you'll shake it up to make sure that the solution is homogeneous. And then you add more water dropwise until the meniscus gets up to the mark, right? In this case, the 1 liter mark, and then you stopper it again and shake it up, and that's it. That's how you'd make your solution. Now, of course, you'd have to do some calculations here, right? And again, for those of you enrolled in my lab course, we did something similar. If you remember, we were working with copper 2 sulfate, pentahydrate, and if you remember, the pre-lab exercise is where you calculated the amount of solute. It's a similar thing that we would do here in this case, right? So that's basically how you'd make this solution. Okay, what time is it now? Okay, I won't go into these examples now. Before you leave, let me remind you that your test number 1 will be next week. And it will be based on chapters 1, 2, and 3. So we're not finished with 3 yet. So basically, once we're finished with 3, then we'll do the problems in relation to those topics that we would have covered. And then your test will be next week, Thursday. All right. So that's something for you guys to look forward to. All right. Okay, so that's it for today, folks. So I'll see you guys on Thursday.